Hi everyone, my name is Juan Maroñas, and in this video I'm going to present the work on calibration of mix-up training for deep neural networks, which has been done with Daniel Ramos and Roberto Paredes. In this work, we study the calibration properties of deep neural networks trained with mix-up, and contrary to other works, we show that these networks are not necessarily calibrated. We provide a solution. The outline of this talk is as follows. We start by introducing empirical risk minimization to frame mix-up. Then we define what's model calibration, and then we argue why Mixup does not provide calibrated outputs. We finally present our solution with a summary of our results. So suppose we are interested in approximating or learning about the data distribution P of t given X with a model, which in this case is going to be a deep neural network parameterized with theta. We can set the parameters theta by minimizing a distance or a divergence, in this case, between the data distribution and our model, which can be done by computing the following expectation, by maximizing the following expectation. But because we don't have access to this distribution, in practice, we substitute it with empirical distribution at the training points, at our observations xn and tn. And we end up maximizing the following empirical loss. The problems of empirical risk minimization is that because we already learn around these data points and the fact that P of theta is an overparameterized model, we know that generalization is compromised, which means that there are no guarantees that our model will actually represent the data distribution. This can be reflected, this generalization problem can be reflected through overfitting, both in terms of accuracy in calibration, memorization, or adversarial attacks, among other effects. So a solution is to use what is called vicinal risk minimization. And the idea here is that empirical distribution is substituted with a vicinal distribution, which is no more than a distribution around your training points. For example, the distribution can be a Gaussian centered at your training points. In practice, you sample from this distribution and you train with samples from the vicinal distribution. For example, in the case you have a Gaussian distribution as your vicinal distribution, you just have to corrupt your training sample with some source of zero mean Gaussian noise. Note that any form of data augmentation can be framed as a vicinity distribution. The problem of vicinal risk minimization in this form is that it assumes that the samples in the vicinity distribution belong to the same label, which is not true in practice. There's no reason why this is true. A mix-up relaxes this assumption by assuming that the samples in the vicinal distribution can belong to other labels. The way it does it is by defining a vicinal distribution, which is the expected value of linear interpolations. In practice, to train with this vicinal distribution, you can sample from it by sample the interpolation coefficient and then interpolate two training points, x1, x2, and the corresponding labels, t1, t2. In this form, the samples in the vicinity distribution have different labels. Then you train your empirical loss with these virtual samples. We now move on to defining model calibration. So how do we take optimal decisions? Well, it turns out that there's a warranty that we can take an optimal decision if we minimize what is called base risk. Here I present what is base risk for a classification scenario. We know that this decision rule is optimal if our model distribution has recovered the data generated distribution. But the question we should ask ourselves is, what does equality here imply? So what two properties has our model, or need our model to approximate or to satisfy in order to approximate the real data distribution? When do we know, or how can we measure that our model has represented this distribution? Well, the first of these properties is what is called the discrimination, which is the ability of the classifier to separate between classes. Note that learning a 0-1 assignment with an overparameterized model can lead to overfitting if we have if our data distribution actually overlap. So suppose that the data distribution, instead of being totally separated, have some source of overlapping. Because we have only access to a sample from this distribution, we might end up being able to separate the whole class, both classes, even though we have some source of uncertainty here. So we can overfit if we have a very overparameterized. Actually, knowing this degree of uncertainty between our data distribution, it's what is called the calibration. So if we assign our confidence based on this overlapping, then our model is calibrated. An example in classification that I always use is the following. A classifier is calibrated if the following happens. If a set of samples is classified toward class A with probability 0.8, then 80% of these samples actually belong to class A. So imagine that calibration just means knowing this overlapping, assigning confidence, assigning probability, depending on this degree of overlapping. If we don't present any overlapping, then our model is calibrated if it assigns 1.0 probability to each of these classes. But if there's some degree of overlapping between the two distributions, then a good calibrated model will take this in consideration. And the way it takes in consideration is by assigning probability based on how the data distribution overlaps, or in other words, on the degree of uncertainty between in the data distribution. Well, it turns out that data augmentation techniques has consistently provided improvements in robustness to OD detection, calibration, or other uncertainty quantification tasks. In fact, there's a recent work that shows improvement in calibration and uncertainty quantification in Mixup. But we should ask ourselves, does Mixup really take the uncertainty in the data into account? Well, as I will illustrate now with a simple example, it doesn't. Mixup can smooth the ultimate predictions of your classifier because it learns data, it generates data between the different classes, but it doesn't preserve, it doesn't generate this data according to how the data is distributed. Hence, we can end up learning an uncalibrated model. To illustrate this, I show this training distribution with two classes, the red one and the blue one. Now I'm going to show a picture with some mix-up samples, where the stars represent the mixed image and the color represents the label. So for example, purple means that there's that the generated label T tilde has 0.5 probability of being to class red and 0.5 probability of being to class. And as we can see here, learning with this data augmentation, we can smooth the prediction of our classifier because we are generating we are teaching our model to learn smooth mappings here, as we see from the different colors here. But as we can see a lot of red, strong red here, around here, or even strong blues around here, which means that Mixup is generating samples that doesn't preserve the structure of the data distribution. So we can not expect to learn a calibrated model in this case by using a Mixup data augmentation. However, it turns out that in some data distribution, well, this depends on the data distribution, obviously, but it turns out that in some data distribution, learning with Mixup can actually help us learning a calibrated model. So here's an example of a data distribution where the Mixup data augmentation had actually provided samples that will end up allowing us to learn a calibrated distribution. If we see this example, a good decision threshold will be placed around here, and as we can see, we have purple color here, which means 0.5 probability assignment with maximum uncertainty. And as we can see here, both classes are overlapping with more or less 50% with a 50% degree of overlapping, assuming that we have sampled the same number of amount of samples from both distributions. Okay, so the prior of our classes is the same. And as we move towards red or toward blue, we see how the samples become more red or more blue. Here I provide another example where Mixup will not provide calibrated distributions. I just put it here if you want to pause the video and take a look at the samples. So as a backup of what we've seen that learning with 0.1 probability assignments overfit if the data presents some degree of uncertainty, because we have an overparameterized model that can learn to isolate each of these samples. Mixup can smooth the predictions in these scenarios, but does not necessarily generate data that preserves this data structure. Solution: why don't we incorporate the data uncertainty in our predictions during learning? How can we do this? Well, we can do this through our classifier. We can use our model, we can use the degree of discrimination learned by our model, because note that the degree of discrimination of our model will tell us how able is our model to separate the overlapping. So how our model has like the degree of overlapping that our model suffers from. And that's what we do. How do we do this? Well, so we propose the ARC loss, which is the ARC loss is a loss that is combined with the cross entropy. Okay, so this is the typical 0-1 assignment that you force in your neural networks. Beta is a hyperparameter that's learned on validation. Here, mu y represents, well, in this case, what we do is, suppose we get a batch of samples and we forward them through a neural network, and we get the highest confidence assigned by the neural network for each of these samples. We partition the confidence range into m bins. So for example, if m is 10, this means that we partition our confidence range into bins that go from 0 to 0-1, 0-1 to 0-2, 0-2 to 0-3, and so on. We compute which of these probabilities of each of the samples lay in each of these bins. And for each of these bins, we compute the average confidence and the accuracy of these bins. Note that the accuracy of this bin will tell us the degree of data uncertainty that is present in our data. So for example, if this is 0.8, this means that it doesn't make sense to force our model to learn a 1-0 probability assignment because there's some degree of overlapping. So we force the confidence to match this accuracy. Okay, this is one of the versions of the loss. We have the other version in the paper. Please feel free to check it. So we minimize this distance, this simple form of loss. So how this works in practice? Well, the proposed loss works by evaluating the cross entropy of the mixed-up image and the ARC loss over the mixed-up images used to create a mixed-up image. Note that why we do it in this way. Well, we actually try to evaluate, we have evaluated the ARC loss both over the mixed-up image and over the separate image. And we found that evaluating it over the separate image is actually what works in general. Well, it makes sense because we've seen that the virtually created mix-up image might not represent the data distribution, and what it actually represents the data distribution is the original images. As a summary of our results, here I show the average of several models, trained with baseline, where I show the accuracy and the expected calibration error. The expected calibration error is a measure of calibration. The lower this value, the better calibrated one. As we can see, Mixup degrades the calibration in many of these situations. And our loss can correct this calibration. Note that there might be examples like Sci-Fi 100 where actually Mixup can provide calibrated outputs, which match other observation from other works. But this is not a general tendency. For a further analysis of this loss, and for example, other observations like how can or why can it boost the accuracy, note that here it also boosts the accuracy, please follow the paper. Thank you so much for attending to this video and feel free to shoot an email for any further